Okay, so up to this point, we've only talked about spin 1/2 systems and, worked with our two basis states, up and down, or plus and minus, whatever you want to call them. And I'm going to introduce yet another notation for those two states, this 1/2, 1/2, and 1/2 minus 1/2. So this is saying that the total spin of our system is 1/2, and the z component is 1/2. And this state, again, the total spin is 1/2, and the z component is minus 1/2. And the reason I'm using this notation is because I want to talk about higher spin systems. So if we had a spin 1 particle, we would have these three states. So for a spin 1 particle, my spin, the z component of my spin can either be 1, 0, or minus 1. So this old notation doesn't really work anymore, but this new notation, we can use that for our higher spin system. So again, this state means the total angular momentum is 1, and the z component is 1. Here, again, total is 1, but the z component is 0, and then here it's minus 1. So we have these three states for our spin 1 systems. For spin 3/2, we have 4 states, and that would range from, again, total angular momentum is 3/2, and the z component ranges from 3/2 to 1/2, minus 1/2 to minus 3/2. And of course, we can write down a general expression for a spin s system. We will label our states by, the same way we've been doing here, by the total angular momentum and the z component, which I'll call, m. And there will be 2s plus 1 states. So, for spin equals 1, there's 2 times 1, which is 2, plus 1 equals 3 states. For 3/2, it's 2 times 3/2, which is 3, plus 1, so that's 4 states, and so on. And the z component of the angular momenta will range from minus s to s. So minus 1 to 1 for the spin 1 states, or minus 3/2 to 3/2 in this state, and in steps of 1. So we have minus 3/2 plus 1, minus 1/2 plus 1, 1/2 plus 1, 3/2. And so this is how we would describe our higher spin systems. And the reason we care about this is we've been looking at a system of 2 spin 1/2 particles. And if you have 2 spin 1/2 particles, well, their angular momenta will kind of combine. So you would expect that our system might behave like a spin 1 system. And we'll see how that works out in the next video. Another thing that we'll have I've talked about it, I mentioned it, I think, the last linear algebra video, are these angular momentum raising and lowering operators that are defined in terms of the Sx and Sy operators. And all they will do, I said last time, is when you act the plus operator on the down state of our spin 1/2 system, it gave us something that is proportional to the up state, along with this h bar, but that's not really important. So you get some additional factor here, but whatever. And then similarly, when we act the lowering operator on our up state, we got something that is proportional to the down state. And this generalizes to our higher spin systems. So for our spin 1 system, again, we'll have if we act our raising operator on the 1 minus 1 state, it gets us to the state of higher z component of angular momentum, so the 1, 0 state. And now we have a different factor, a square root of 2 h bar, but whatever. The important thing is we act s plus on 1 minus 1, and we get something like 1, 0. And then similarly, when we act s plus on 1, 0, we get 1, 1. So we climb these states. And if you act s plus on 1, 1, then you get 0, because you can't raise the z component of the angular momentum anymore. because the maximum component of your angular momentum along the z direction is just the total amount of angular momentum you have. And then similarly, s minus on 1, 1 gets you to 1, 0, s minus on 1, 0 gets you to 1, minus 1, and s minus on 1, minus 1 gives you just 0. And this generalizes to, a system with spin s that will have, states, these Sm states. And when you act s plus and minus on it, you will get some kind of nasty looking coefficient out in front. But the important thing is when you act s plus, you get a state where, you have s m plus 1 and s minus acted on the state, you get a state that is s and m minus 1. So despite how nasty this coefficient looks, this is really saying something. It's just saying what we've seen here. The s plus operator takes you up in the z component of angular momenta, and s minus takes you down. And another thing we can have is that all of this will also apply to a spin 0 system. So if we go up here and look at this general expression, if we take s equals 0, that tells us we will have 2 times 0 is 0 plus 1, so we have one state, and the m value should just be 0 because it has no angular momentum. So it tells us we should have just one state. And if you act s plus and s minus on this state, you should get 0. And that you can just check from this expression. If s and m are both 0, then this term is 0, so you just get nothing. And we'll see how this all comes into play when we take another look at our system of 2 spin 1/2 particles.